vPC, virtual port channel. We learned that vPC takes the multiple switches, but when I say multiple, it's not multiple, it's multi-chassis, but not more than two, just two switches, and combines so that you will have one common switch ID to negotiate either channel with the downstream. So this box, two boxes that participates in this vPC, they're called as vPC peers. Let me name that as N5K1, Nexus 5002, N5K. Those two are called as vPC peers. And we also learned there will be one keep alive link and one peer link. Let me draw the keep alive link with the dotted lines and peer link with a straight line. Yeah. Keep alive link and peer link, two special links for vPC. And we got switch which supports on mode or LACP mode. It need not to be a switch also. The below one can be a server. But let's focus on switch. It's basically same function. If it is server, we call it as NIC teaming. Servers also do support LACP, if not at least on mode, the static on mode. That doesn't matter whether you use on mode or LACP for this vPC members. Now these two switches on top, only for the vPC sake, they are combined as one single switch. What is the advantage? Advantage is the traffics are going to flow through both the links, this as well as this. The traffic coming from here will go through both 5K1 and 5K2. When we don't have vPC, we can't do this, right? Due to the STP's blocking, to avoid looping, we will not be able to utilize both the links. Now, with vPC, we can use both the links, dual active links. What does it provide? It provides more bandwidth now. Earlier, without vPC, only half of the bandwidth. We were not able to use both the blue links, but now we can use both the links, dual active links. So as a result, increased bandwidth. So here the links are not subjected to STP. That's how the increase in bandwidth. Next is, if this link goes down also, you will have all the traffic that was earlier going through this way, now it will go through this way. What does that mean? We got a redundancy. Because you got dual active path, we got a redundancy. Not only that, if any one of this device goes down or a link goes down, you have no problem. If this link goes down, is there any problem for the traffic flow? No. The traffic which was earlier going this way, it's going now this way. Or if this switch goes down, no problem again. So there is no single point failure. Turn C. No single point failure. Yeah. So these are the advantages. Now these things we saw earlier. Now we are going to see more deeper how it works. You know what it will do? It will, one of the switch will be elected as the primary switch. It can be any switch. One of the switch will be elected as the primary switch. Let's say this is primary. The role is primary role. This is secondary. Now what is the difference between this primary and secondary? Primary will take care of the control plane traffic. See, it's not secondary going to sleep and primary will be taking all the load. No. Both are going to work actively. Both are going to be a forwarder. Both are going to actively carry traffic from south to north and north to south. So the data plane is up on both. But the control plane is going to be taken care by the active device only. Yeah. So the data plane means, the forwarding plane obeys the control plane. Primary device takes care of the control plane, which means it is the primary device that is going to decide for what all MAC address the secondary device should be responsible for forwarding, and for what all MAC address traffic the primary will be responsible. You got two switches here. Both should share the load. They should understand each other. Both switches should have an understanding. Both the switch should have an understanding. Only then the traffic flow will be normal, peaceful. If one switch says you take care of all the even number MAC address, I'll take care of all the MAC address that are learned odd. Like first MAC address, you take care of. Second MAC address, I'll take care of it. Third MAC address, you take care of it. Fourth MAC address, I'll take care of it. So when the primary device sets this rule, and when secondary device follow it, no problem. There won't be problem, because at the same time both the switch is not going to take responsibility for a single MAC address. For each MAC address there is a dedicated upstream switch there. MAC address A, if it goes via 5K1, MAC address B, if it receives packet, let's say MAC address A is taken care by 5K1. Assume this is the MAC address of some computer here. 5K1 says I am responsible for this MAC address. So on switch 1, to reach AA, this is the port via which the packet will be forwarded down. Likewise on this 5K1, this will be the port for AA. If any packet coming from internet, If it wants to go to AAA, accidentally if it goes here, secondary switch knows that I'm not supposed to forward it down here. I'm not supposed to forward because I am not active for that MAC address. I'm active for BBB. If BBB comes as the destination, I'll take care of it. I'll forward it to BBB computer. But for AAA, I'm not responsible. So it will send the traffic that it received from the orphan port. What is orphan port? The port that are not the member of vPC. We learned that in the previous class. Same VLAN, but not the member of vPC. Member of vPC belong to VLAN 10. This orphan port also belong to VLAN 10. So traffic comes in. It will forward to its VLAN member. That VLAN member happens to be a vPC member here. So switch 5K2 says I'm not responsible for this, so let me send it through the peer link so that 5K1 will forward it down here. For this reason, I'm telling something very important now. For this reason, all the VLANs that are allowed on the member port should also be allowed on the peer link. All the VLANs that are allowed in the member port should also need to be allowed on the peer link. Fine. So far what we have seen is there is one primary device and one secondary device. It is only for the control plane. For the control plane, two people cannot control one. That will be always problematic. If two people tries to drive a car, what will happen? Accident. Only one driver, one steering wheel. Whatever the costly car you take, there is one steering wheel only. Only then all four people sitting in the car will be leaving the next day. They will leave for next day. If two steering wheel is given, finished. All who sitting at the back also, life is not guaranteed, not only the driving people. So control plane cannot be two, can be only one. That is why this primary and secondary election, primary and secondary role. Now, both the switch cannot control, only one switch can control. That will be taken care by the primary switch. Anyone, whichever came first will be the primary switch. Whichever you configured vPC first, it will take the primary role. Now what if this primary switch goes down? What if this primary switch goes down? All the traffic that was going earlier via primary switch now will go via the secondary switch, and secondary switch will take the role of primary. So the traffics are not getting disturbed. All the traffic now goes through the new primary. If the old primary comes back, it will go as secondary only. What does that mean? It cannot take the primary position. What does it mean? It is non-preemptive. Preemptive. The primary secondary role is non-preemptive. What is preemptive? If this N5K1 would have claimed the primary position back after when it comes back, then it is called preemption. But because the primary is already there, NK52 is the current primary, 5K1 will continue to be will accept to take the role of secondary. Why? Because it just came up. It went down for some time and it has just came up. So only 5K2 knows the current scenario. 5K2 was alive for a long time. 5K1 just came in. We don't know much MAC addresses, but 5K2 knows all the new MAC addresses and many more. So 5K2 can be a control plane now. 5K2 will say, okay, fine, I take care of these MAC addresses, you take care of these MAC address traffic. So it is good that the primary secondary role is non-preemptive. Fine. Now let's go a little bit backward and we'll discuss more about the keep alive link one more time just to recall. The keep alive link is a layer 3 link, as I said earlier. It's a layer 3 link. The purpose of this link is just to give a heartbeat, just to tell that the switches are alive. Switch 1 knows that switch 2 is alive through the heartbeat that is coming through this keep alive link. The keep alive packets come. It is good. If you don't have keep alive, what will happen, If you don't have keep alive, what will happen? When this peer link goes down, this switch will think that the other switch is down, but the other switch is alive. The switch is currently secondary. Because the peer link has gone down, it thinks that the other primary is gone down, so this will also claim to be primary. When both are primary, this also will say, I'll take care of all the MAC addresses. This also will say, I'll take care of all the... It is called split brain issue. Split brain. Two brains. Like two drivers driving one car with two steering wheels. That will spoil. Yeah. To prevent split brain issue, if you would have kept the keep alive link, when the primary link goes down, the keep alive link will tell, hey, the primary is still alive. Don't take the decision of what? Decision of becoming primary. The real primary is still up. Yep. So it is a kind of second verification. Second verification. When we go to new place, we ask address to someone, and when they tell a path, we keep going, but after some time we get a doubt. So we cross check with the second person whether the route that we are taking is correct. Likewise, a kind of second opinion. Keep alive links, they're not really helping to synchronize between these two devices. They are simply giving the heartbeats. It keeps going, pum, 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 it keeps going. The keep alives keep going. Even when the peer link goes down, the switches very well know that the other switch is still alive. So the secondary switch will not try to become primary and cause split brain issue. Keep alives are good. But there is a recommendation for keep alive link. What is that? See, if this peer link and keep alive link are in same VRF, what will happen, if they are in same control plane, if they are under single routing table, if something goes wrong with that routing table or with that module, along with the peer link, the keep alive link also will go down. Then there is no point. See, if you take N5K, Nexus 5K, it will be like this. You can take the keep alive from this module, let's say module 5, and you can take peer link from module 4. Why? If module 4 goes down, still the peer link will be alive. If I take both the peer link and keep alive, you understood, right? When the module goes down, you lose both. Then split brain will happen. So it is recommended, if you have multiple modules, put them in different module. The keep alive link and the peer link in different module. That's one. Another one, try to put them in different control plane, like out of band management. Out of band management. What does that mean? Out of band management. All the interfaces are in one VRF, but this alone is in another VRF. Likewise, we got management 0 under the VRF called management on both the switch. So recommended to use the management port which is already there in the default VRF called management, so that this will be separate control plane, the other interfaces will be in separate control plane, and this will be in separate control plane. That is what we call out of band management. We are not mixing together, it is out of the bunch of other interfaces. If that VRF goes down, this VRF will be still there, helping to manage, helping to tell this two switch that both the switches are alive, so continue with the role, don't change the role. So that's about the keep alive link which we saw earlier. What about the peer link? Peer link is a high speed link. This is for fast synchronization between, what synchronization? MAC address synchronization between this peer switches. This peer link is to synchronize these two switch quickly. That's why it need to be high bandwidth link. Practically, if you see, we'll take 10 gig 2 links and bundle it as peer link. 10 gig 2 links, we'll put it in one bundle. That's how we do. That's why peer links need to be a high speed link. That's how we achieve that high speed. And this is used for forwarding the traffic, sharing the updates of each switch to one another. It is a kind of back panel between these two switches. It's a kind of a back panel. What does it mean? You are taking this motherboard and this motherboard and combining it together. Back panel. Back panel. So sometime the broadcast traffics are carried in this peer link, multicast traffics are carried in this peer link, right? And also when some link goes down, say for example all the traffics were going like this early, but this link cut off, so now the traffic should go like this. So the unicast will also sometime, when the link failure happens, it will be sent via the peer link. So peer link, will they carry the user traffic? Of course, yes, they do. When the link fails, in order to go upward, BBB is responsible. BBB 5K2 is responsible for BBB, so it cannot go like this up. It cannot go like this. So it will take this switch and then take the peer link and then go up, because for BBB this switch is what responsible. So unicast, broadcast, multicast, all these are sent via this peer links. Sometimes broadcast, sometimes multicast, whenever it's necessary. And also, as I said earlier, for MAC address synchronization between the switch, why the MAC table need to be synchronized? For fast recovery. How? For example, if the switch goes down, all the MAC address of this switch also need to be now taken care by the primary device. So when they are having the synchronized MAC table, the recovery will be faster. Otherwise, this will start learning new MAC address that will take time. So fast synchronization and carrying unicast traffic when there is a link failure, carrying broadcast traffic, multicast traffic, acting like a back panel between these two switches. All these things are taken care by this peer link. So we have seen peer link as a layer 2 ether channel between this peer, because we need fast link. Now, we also learned in the previous class that this vPC has got two different type of ports. There is an orphan port and there is a member port. There is a member port. This and this are member port. Because vPC is done on that port, and these two are vPC peer box, primary and secondary. We got a keep alive link, we got a peer link. Yep. So member ports are the ports which is configured with vPC, whereas the orphan ports are not configured with vPC. This is just a normal port. Orphan ports are simply normal port without any vPC configuration. That may be connected to a router here on the top, or another switch, can be connected to some core device or a distribution switch sometime, depends. Orphan ports are like that, but the member ports sometime they are connected to a switch like this, sometimes they may be connecting to a server down here, depends. You remember when I was talking about peer link, I was mentioning this. I want to remind you, whatever the VLAN that is allowed in the member port, if I have VLAN 10, VLAN 20, VLAN 10, VLAN 20, that need to be also allowed in this peer link. VLAN 10, VLAN 20, very important. Right, that's about the orphan port and the member port. Okay, one more thing is, when you configure a vPC on these two ports with this VLAN numbers, trunk, so on, vPC will check the member ports for inconsistency. It will check whether is there any inconsistency. What is the inconsistency? Some mismatch in configuration, something wrong, not same, not all the configurations that you have done here. If it is not matching on here, then it is called inconsistent. So vPC will check each member port for inconsistency. If it finds, depending on what type of inconsistency, the action will be taken. In inconsistency, there are two types of inconsistency. Type 1 inconsistency, type 2 inconsistency. If type 1 inconsistency, what does it? Inconsistency, again, to put it simple, error. If type 1 error is found, the primary switch will keep the ports up, but the secondary switch will block the port, disable the port. Disable is the right word. Disable the port. So when we configure, if there is a type 1 inconsistency, type 1 is a serious inconsistency. It's serious. Something very important is not properly configured. So this port will be down on the secondary switch. The secondary switch member port will be straight down. If type 1 error is found, the primary switch will keep its port up, whereas the secondary switch will disable its port. Will the traffic flow stop? No. All the traffic now flows through the primary switch. That is about type 1. Type 1 is common if some of the configuration does not match on both the switches. So we need to make sure we configure properly on both switches, the same configuration. If one is configured with some policies, if the other one is not having the same policy on the port, or one side you say trunk, another side access, something like that. You know, for port channel, both the links should be of same speed, same duplex, allowed VLANs, all the steps are there. So if they don't match properly, then there is going to be inconsistency. If it is type 1, then secondary switch side will be blocked. The member port on the secondary switch side will be blocked. If it is type 2 error, both the switches will keep the ports up, but there will be only syslog messages generated. So type 2 is not a serious error. Type 2 inconsistency is not a serious inconsistency. Both the switches will be in a forwarding state. Both the links are active, so both the switches are forwarding switches. Only thing is syslog will be generated and sent to the syslog saying that this particular configuration is mismatching. Maybe VLANs. You allowed VLAN 10, 20, 30 here, but here 30 is not mentioned. That is type 2 inconsistent. It's not a serious issue, but it is an issue. vPC will work fine for VLAN 10 and 20, but for VLAN 30 it will generate a syslog. So these are things about inconsistency that vPC will check on the member port for inconsistency. Next is when we learned yesterday in the previous class about vPC, we learned that between two switches port channel is possible, but if I have two upstream switch and totally if we have three switches, then port channel is not possible because the switch ID coming from here and the switch ID coming from here won't be same. According to switch 3, it should receive the LACP packets from the same switch ID, but switch 1 ID and switch 2 ID is not same because they have different MAC address, they have different priority sometime. The bridge ID is not going to be same. So switch 3 expects the other end of the wire to have same system ID. Same system ID is what needed for LACP. So when you do vPC, what happens is this Nexus switches that supports vPC, it uses the domain ID that we give. When we configure vPC, we give a number as domain ID. And it needs to be same number on both switches. We say domain ID 10, vPC domain ID 10. It takes the domain ID that we configure and it generates one MAC address. Both the switch is configured with same domain ID. So both will generate one same identical MAC address. Because both are from Nexus family, they are designed to generate same output. If you give 10, both will generate same answer, same MAC address. So they generate a similar MAC address, same MAC address. So that is going to be used as the system MAC address now. Every switch have got their own MAC address. That is not now considered. Using the vPC domain number, domain ID, now both have generated a MAC address. That becomes the system's MAC address now. So both the switch now will generate its own system ID, which is equal to domain ID plus the newly generated system MAC address. Newly both have generated same system MAC address plus the domain ID both switch have got, definitely they will have same domain ID. That is what becomes the system ID now. And also LACP will look for priority. Both should have same priority. System priority. Now if you say 4096, here also it should be 4096. Same. Only then the system ID that both generate will be same. When it comes down, it will be same system ID. So system ID should be same, the domain ID should be same. When it is same, now a virtual system ID will be generated by using the domain ID plus the newly generated system MAC address. As a result, this two switch will be now seen as one single switch. It is now seen as one single switch. And now LACP is possible. One more thing is important. In our network, if you are having multiple vPCs, let's say I have one switch here, another switch here, forming vPC with this. And I got another switch also here, another switch also here, forming vPC. And somehow this is also connected here, this is also connected here. So we need to be very careful that they don't mix and cause confusion. So what we can do is, for this we can give a domain ID 10, for this you give different domain ID, don't give the same 10. Why you tell? Why? Because they are going to use the domain ID and generate a MAC address. And the MAC address will be now causing issue. So should use different domain ID. Fine. Next. When we have 3 switches like this, usually loop will occur. Well, let's make it more interesting. Let's say we got a server here. We got another server here, different color. This server is having vPC. This is having another vPC. Now we got a peer link and a keeper link. Let's say the server 1 is sending some traffic. And now the traffic goes this way and this way. What will happen? Duplication of frames, loop. It goes here. Another copy is coming like this here. So this causes a loop. But this never happens. You know why? If a frame is received on the peer link, see? The frame goes here. It goes this way as well as this way. The one which goes in this blue line will be successfully reaching here. But the one which is going via the peer link, this is the rule. What is the rule? vPC will not allow, if the frame is received on the peer link, is it receiving on the peer link? Yes, switch 2 is receiving the frame on the peer link. It will be delivered only to the orphan port. See, this is an orphan port. It will deliver to that orphan port. But if it needs to go via a member port of any vPC, it won't allow. The frame needs to be delivered to a member port. The frame will drop. If it needs to be sent via the member port, it will drop. It won't allow. If when a switch receives a frame via peer link, and if that frame needs to be sent via a member port, it won't allow. It will simply drop. This is how, even though we don't have spanning tree, the loop is prevented. So to orphan port, there is no problem. The packet that is going this way, if it is a broadcast, it goes this way, and it goes to the orphan port, not a problem. But if it goes to a member port like this or like this, then loop will occur. To prevent loop, a flag is hoisted. When a packet enters the peer link, it will go with the flag. The frame will have a flag saying switch 2, switch 2. This you should not send it to a member port. Then switch 2 will not. Right? Fine. Now, because I enabled vPC, it doesn't mean that spanning tree is disabled on these two switches. Switch 1 and switch 2 still runs spanning tree for other ports, not for this member ports. For all other ports, for all other ports, the spanning tree is running. But the problem is, on the member ports, you will not receive BPDU from a secondary device. Why? Only the primary device is doing the control plane job. So if this is a primary switch, the secondary, the primary switch will send the BPDUs. Secondary switch won't. but it is not healthy. For sending VPD both on primary and secondary, what we need to do is we need to use a command called peer switch. That's all. Peer switch. There's a command called peer switch. When we configure, I'll show you. So sometimes you will feel when you configure like why are we configuring this command? The command is just to make both primary and the secondary to take part in STP. Will there be any problem? No, because they both have the same bridge ID. You remember, they got both same bridge ID generated with the help of domain number. So it is good to have BPD on all the links from both the switches. For that, we just put one command called peer switch. It's not one switch, it is peer switch. Is it clear so far, or do you have any question up to now?
No, it's clear.
Now we are moving on to
No, it's clear.
failures in vPC, troubles in vPC. Got 1, 2, 5 keys, and then I got catalyst switch. One in different color. So this is going to be N5K1, N5K2. I'll simply call this as catalyst 3. Now, what if one of the member port goes down? We discussed this already. This is one of the failure scenario. What if one of the member port fails? Not a problem. The traffic will start flowing via this link. There won't be a problem for the traffic flow. Fine. What is the next scenario? What if the entire switch goes down? If the entire switch goes down, then also no problem. All the traffic will go via this 5K1. Let's say this is a primary switch and this is a secondary switch. Now what if the primary switch goes down? Not a problem now. The secondary will take the role of primary. And what if the primary, the old primary comes up? It will become secondary. What we understand, there is no preemption. We discussed this earlier. Next. Next is, what if when the peer link fails? Let's say this is peer link. This is keep alive. When the peer link fails, you remember I told you some time back, when the peer link fails, keep alive link will be keep on sending hellos, right? The keep alives. So switch 1 and switch 2 knows that both the boxes are up. The other switch is not dead. It knows. But to prevent loop, because they are not synchronizing now, the peer link is down. They cannot synchronize. The primary cannot have control over the secondary box, because through the peer link only the synchronization of MAC table and all the control signal goes. For that reason, it will simply block the member port of the secondary switch to avoid loop. Because when new MAC address comes, it will cause loop. So to prevent the loop, the member port on the secondary switch will be blocked. And primary switch will continue flowing all the traffic. No problem for the traffic. Understand? When the peer link goes and when keep alive is present, peer link goes down, keep alive is still available. What will happen to the traffic? Nothing will happen. All will flow via primary because the secondary member port will be blocked to prevent loop. But what if the peer link goes down and also the keep alive link goes down? When the peer link goes down, what happened? This is discarded. We just now saw, right? When the peer link goes down, the member port of the secondary switch will be disabled. And now the keep alive also goes down. Is there any problem now? No problem. Because already the secondary switch member is disabled, so there is no problem. All traffic will be peacefully going via the primary. No problem at all. When peer link goes and then keep alive goes down, no problem. But if the keep alive goes down first, keep alive has gone down, and now the peer link also goes down. Because the peer link has gone down, there is no keep alive also. These two will start calling themselves as primary. And this will result in split brain. To avoid this only, early in the beginning I said, try to keep the keep alive in a separate VRF, in a separate module, so that this will never happen. If this happens, split brain. Then the administrator need to log in to troubleshoot. This should never happen. Which should never happen? Keep alive went down and primary also went down at the same time. That should never happen. If it happens like this, it is okay. Peer goes down, so this is blocked, and then keep alive going down, not a problem for the traffic. But when the keep alive goes down, no blocking happens anywhere. But when the peer link goes down, because there is no keep alive, 5K1 thinks that the other switch is dead because there is no confirmation for the switch 1 to say switch 2 is alive. Both the links are down. There is no confirmation. There is no signaling. So switch 1 says, I am no more a secondary because that other switch is dead. I am primary. And this is called split brain. And this should never happen. Okay, this is a very rare case. But make sure this never happens by putting the keep alive and the peer link in different IO module, the physical module, and also put them in different VRF. That brings us to the end of vPC theory. Practical some other day, all the labs together we will do. And in our next class, we are going to see some new topics. Do you have any question on what we have covered in vPC? You may ask now.
No.
Right. Thank.
No, I'm clear with it.